Hello students. So, in this lecture, we shall be discussing about surface. Now, there is a saying that God made, s- yes, there's a saying that God made matter and the devil made the surface, as shown here. Now, why this statement comes into the picture? Because the properties of the surface they they become so much different from the bulk that and it's also unpredictable. That's mainly because of the fact that the surface atoms. So whenever we are looking into a surface system, we basically are talking about the surface atoms whose properties will determine how the surface will behave. Now, this is a surface atoms are present on the surface. Now, the difference between these atoms and atoms present in the bulk is there is a loss in 3D bonding, and in these atoms they are bonded uh, along the three sides x, y, and z axis. So there is a bond here, there is a bond here, there is a bond here. But these surface atoms, they actually on the z-axis, that is above these atoms, there is no bonding. So that makes these atoms to be in a energy state, higher energy state compared to the bulk atoms. This is higher energy state. Now, as these, there is the a system always comes, always tries to be in a low energy state. So that is how these atoms make arrangements which are known as relaxation and reconstruction to come into a low energy state. The relaxation takes place along the vertical direction, where the atoms they are at a further away, they are at a larger distance from the bulk atoms, and the reconstruction takes place along the horizontal directions, where the arrangement of the atoms, the distance between the atoms, it actually increases. Now, also there are dangling bonds. Dangling bonds means those bonds. So those bonding sites which are yet to be bonded with another atom. So if you look at any atom, so it is bonded in the x-axis, it is bonded in the y-axis. This is your x-axis. You might be experience a bonding here. There also there is also bonding in the y-axis, but there is no bonding in the z-axis. So this is actually vacant. This is just about trying to find a bond. So these are called dangling bonds. So these dangling bonds also make the surface react more reactive than the bulk atoms. Now, coming to the reconstruction that takes place in the surface example, a perfect example of a surface reconstruction is silicon 117 cross 7. So, what can be assessed by just looking into this symbol is that we are talking about a surface of a silicon 111. So, in the bulk, this is the crystallographic orientation. Uh, Whereas in the surface, there is a loss in periodicity, 3D periodicity. So from three indices, you are coming to only two indices. And also, 7 cross 7 means that those two indices or those two atoms, they become 7 times apart from each other. So that this whole symbol means. Now, this silicon 7 cross 7, the structure was observed under scanning tunneling microscope. This is an example. This is a picture of a scanning tunneling microscope at ISC's Calcutta. You can see. it is basically you get very high vacuum. You need to have ultra high vacuum as 10 to the power minus 11 torque to get to be obtaining such type of surface. Then a silicon surface always has a native oxide layer. Okay, so a silicon, you take a silicon, any silicon surface will have a native oxide layer. So this is a silicon surface. It will have oxide on its top, right? And the oxide thickness is around 250 nanometers. Okay. So if you would like to see the reconstruction that is taking place on the silicon surface, you need to first get rid of this oxide layer. And this is done by a process called the resistive heating. So this is the oxide, as you can see. So by allowing current to pass through this oxide, you actually make it disappear. This is called resistive heating. And after this resistive heating has taken place, then the process of reconstruction automatically starts, and you get to see a 7 cross 7 structure. This is a 7 cross 7 structure observed under the scanning tunneling microscope. Now, this notation is this notation of representing a surface. This is called Wood's notation. Wood's notation. Whereas there is another way by which we can represent a surface, that is called the matrix rotation. So we have initially we can represent it by, say, these are the reconstructed silicon surface, and it is related to the original surface A1 and A2. So this was original work surface indices. So we are only having three instead of having three lattice parameters as in the case of bulk. We are having only two lattice parameters related to the length. Now this is again related to, we can represent it by a 2 by 2 matrix. So the matrix simply tells you how, so if there are two atoms at the surface, how they have been, how they have changed their position with respect to x-axis and with respect to y-axis. This is what these atoms, this notation tells you. So there are, if there was E1 and E2, first here is E1 and E2 atomic positions. So if it has moved, say, a certain distance in the x-axis and a certain distance in the y-axis, so it again will be presented by two elements of the matrix, say these first two elements, and this again will be presented by the two elements. So there are four elements, so it makes a 2 cross 2 matrix. So this is the matrix notation of representing the surface. So there are two notation. One is Wood's notation, where you simply write the distance between the atoms after reconstruction, and also there is one angle associated with it. So in this case, since it was 90 degrees, so it was not written. Usually, you can find surfaces where the angle is, say, 45 degrees or 30 degrees. So that also comes under the Wood's rotation. And the matrix rotation, there is no angle, but only the ratio of the distance that the atoms have moved after the reconstruction has taken place, represented by a 2 cross 2 matrix. Now, the scanning, this was all about the surface representation or surface atom representation. Now, the process of seeing or observing or getting the image of these reconstructed surface is through STM. And so when we say STM, when we say STM, so there are two processes that are taking place. M stands for this microscope, and the first two letters, this stands for the scanning, and this stands for the tunneling. Scanning is done along the x and y axis to get the image of the morphology, and the process of tunneling is the reason of getting the image. Now, what is actually tunneling? Tunneling is basically, if you look into the quantum mechanics, if there is incoming wave function psi having energy which is less than the barrier energy, so and the system is subatomic. So according to quantum mechanics, there is a possibility that due that the atom, the wave function representing any particle, it can tunnel through it. What is the basic idea behind it? Idea comes from the Schrodinger's cat, as you can see. So, it is based upon the fact that if a cat is inside a box, the probability that it can be outside the box makes it outside the box. So the same principle is being applied here. So if the electron, so this is your sample surface, sample, and this is the tip. So and there is a certain gap between this, between these two. So this gap is actually represented by this energy barrier. Now, even if these are not in contact, what has been found is that electron tunneling takes place between these two states and these two areas, whether it is goes inside or it goes outside, whether it is from the bulk to the tip or it can be tip from the bulk, depending upon the bias that has been applied. Now, so here also the probability that the electron can here or can be outside the barrier, can be at a distance on the other side of the barrier, makes the electron present in this barrier, because and this probability is actually represented by wave function square. So this is the wave function. So it's square, it represents the probability. Also the intensity dies out, as you can see. So this is the area. So as the electron gets tunneled through this barrier, so the amount of intensity or that will be present on the other side of the barrier depends upon how great is the barrier. So it's obvious that a higher energetic barrier will dampen the wave function accordingly. So that means, what it actually means, that there are different gaps. So this is the electron, this is the surface, and this is the tip. So when the tip scans through the surface, it's not that a gap between them is uniform. So the gap actually varies. So due to the variation of the gap, the probability or the dampening also depends upon this gap, because higher is the damping, higher is the gap, lower will be the damping and lower will be the intensity. Now, as the intensity of the current depends upon the probability of the electron, so since we have we actually get a morphology of the surface, which represents the amount of electron tunneling that has taken place. Now that is processed, and you get the image of or the morphology of the surface. So there is an higher intensity means the gap was smaller, and lower intensity or means the gap was larger. So that's how you get a gap. So this is a typical surface of an AU100 surface, and this is a two-dimensional monolayer of another material which is called a goldine. So it's an analog of graphene. So graphene is basically one carbon layer. So goldine is one gold layer. So this newly developed material, goldine. So STM has also been developed to get this sort of structure. And this is the typical graphene that we have just mentioned. So graphene is say few atomic layers or the few monolayers of graphite, and it is called a zero band gap semiconductor. It is initially it came into existence. It can be manufactured came into existence by the process of Scotch tape method. Although there are novel chemical methods of production of graphene has recently been developed, graphene and RTO. And the property of graphene, it again depends upon the chirality. It is considered to be stronger than steel, flexible like a rubber, lightest and thinnest device can be made possible. It has got a long battery life and it is also biocompatible. So all these properties they go for this material graphene. So it also becomes a 2D material like the previous materials that we have discussed. So when we are talking about the surface, we are basically referring to two-dimensional materials. So a good example of these two-dimensional materials is graphene, then we have goldene, and this all the surfaces that can be represented by these methods, like the silicon one-on-one surface and gold, and there are a lot more. So this was all about surface. We'll continue. We'll take up each of these topics in details in the following lectures.